So this is just a quick little session on for those people who are MPI programmers as well. How many people here do MPI as well as OpenMP? Oh, okay, a fair few, but not too many. So if we want to do hybrid programming, why would we want to do it, etc., and how do we do it? So for message passing, we can do on-node communication, but you may still have to buffer the data as you transfer it around, whereas in shared memory it's much easier. On-node communication is just a memory copy, but the operating system can sometimes get in the way by forcing you to put the memory from one process into a common area that then the other process may have to get a second copy of before it can come out. Well, you may get a lot of copies with MPI processing buffering. This obviously consumes your memory bandwidth and slows down the communication, even though all you're trying to do is just take some data from here to there. Remember what we said about processes and threads. The difference is that threads can see the memory of other threads. Processes completely distinct unless you do special things. With MPI, typically the operating system does, the library itself does that special things for you. Some libraries exist to minimize the transfers, taking advantage of some special kernel features. And these ones that are normally built into your MPI library, you don't have to worry about them. So KNEM is exploited by OpenMPI. We don't have OpenMPI on these things. XPMEM is typically the one that would be used by Cray. And this is just a special way of saying, I will now allow you to make a single copy into a memory region and then back out again into the other processor's memory where you want to do your send and receive to. OpenMP Threads can avoid these problems because you're just reading and writing to memory of the same process on the same node. So here's an example of how you might write these things in Fortran. Just to say, how fast would these two things be? This is the way you would do send-receive between two processes. You'd have a send array and a receive array. We're just swapping this data around, etc. Whoops. And here is how you would do the same thing in OpenMP. You can just quite simply copy from one place to the other. The speed difference may be 2 times as fast because you can avoid a copy, but in some cases it can be up to 4 times as fast depending on what's happening. Particularly also because there can be overheads anyway of setting up this XPMEM. It can be slower in terms of an initialization cost than even if you wanted to just send 1 or 2 bytes of data. So we've got the process memory model we've mentioned before about the text, the heap, the stack, and so on. In addition, because of those processes being separate, the fact that you have multiple MPI processes on the node means that you've got to have separate buffers that MPI would want to use. So oftentimes when you see your MPI implementation, there are buffers, and it may be buffers just to get incoming data traffic and outgoing data traffic. They may allocate some data, some buffers for I/O traffic, for example. You may set that up as well. This can actually start to consume quite a lot of your memory. Now, some of this may be configurable, but there's still likely to be some space needed. If we only have one MPI process and a lot of threads, we only have one copy of the buffer to worry about. There are some times as well, because of the way that you need to know about other MPI ranks along the entire system, that the memory requirements grow with the number of MPI ranks. If it's linear, it's almost we can get away with that, but these things really aren't that scalable. Because as you go to the sort of scale of the largest machines in the world, such as if we take the largest scalar machine, as in not GPU's machine, then we have an IBM Blue Gene Q machine over at Lawrence Livermore 1 National Laboratory that's got 1.5 million processors. And to get good performance, you need to run 3 million threads, which could be MPI processes themselves. If they were MPI processes and you needed to keep some data about every other process on the system, you were already starting to use quite a lot of memory. There's 3 megabytes per byte that you need to keep about all the other processes. So keeping things down in terms of number of threads, using threads instead, is obviously an advantage. And you may actually have your own libraries that require some extra buffer space. So separate processors need that address space. Every time there's a fork on the system, it copies all this space. Threads, much more lightweight. We only need one copy of these things. So using MPI OpenMP as a hybrid model can reduce that memory requirement, that overhead that you would otherwise require. And there's a number of people who use our systems and use other people's systems more than probably we expected when we started looking at MPI OpenMP, who do it mainly for the memory, mainly to actually get access to more memory per process, and not actually for any speed up or increase in scalability. So if we also look at then at what that means in terms of the data we need within our application, as well as all these extra little overheads that sit around to the side, then we can see that quite well by looking at MPI processes with halo regions. So in this particular case here, we may have, say, 8 MPI processes on a node, for example, and here they've got some data they want to work with, but they have to have a halo region that this bit here that's been calculated by this process, similarly this bit here has been calculated by that process, so they can do their work effectively, okay? Typically you might have some boundary, 10 by 10 square or whatever, but you need a 1 or 2 pieces of data to surrounding it for your finite difference scheme, etc., as we were looking at with Laplace examples. So these halo regions need to be copied frequently, means we have to have MPI sends and receives and so on, as well as there's just data there. This is one example. Many of other data structures could have the same sort of approach. So if we have OpenMP Threads, well, we can get rid of the halo regions within the node, or at least within the range. It could be a NUMA domain or whatever, where we're going to use the threads instead of the process. So we still have the outside domain. All the internals, the actual computation stays the same. We're not going to save anything from the computation, probably, but we don't have to communicate as much, which is quite nice. Plus also, we save a lot of storage, okay, simply by not having these halo regions that we would have to transfer between things. Now we use Amdahl's law for strong scaling, and it tells us part of the tale, but we actually have a variety of different things. It's not the case that, as with when we talk about Amdahl's law, that we're just talking about compute being changed. There's actually a number of different ways that applications scale. The compute part may be the bit that is relative to Amdahl's law. You increase the number of processors, it could be processors, it could be threads, could be processes, and then you decrease the amount of work per process or per thread. But your communication may go down differently. It may be that your I/O doesn't go down at all. So here's an example. If we look at a domain decomposition, just as we had before with some halo regions and so on. If we have M processes and we split this into, P processes, and we split this into 4 P processes, then what we can tend to do is we get 1/4 of the number of grid points per processor, but only 1/2 of the halo region, the perimeter. That only goes down by half. We've actually got twice as much halo region overall over here now. So what this means in terms of our ratios of processes, computation scales order P for P processes, in this case in a 2D case. So we may have a minor scaling problem, issues to do with memory bandwidth, vector length, software pipeline, the sort of things we've talked about over the last couple of days. The communication scales order root P processes. It doesn't go down at the same rate, okay, because the halo regions don't shrink at the same rate. And then actually we also can end up with something like I/O and other serial parts which have no scaling at all. So Amdahl's law, which is what we normally think of here, actually isn't necessarily the complete tale, because we do have to take into account communication. And so if we then have, as an example, some MPI work, but now we can bring it into our OpenMP world, we can actually get a benefit out of this. So if we assume we've got a cubic 8 by 8 by 8 cube with a 1-element halo, that becomes 10 by 10 by 10 points that we have to take account of. Well, if you do the maths, then you will find that that's 512, and that's 1,000. So approximately 50% of that is just halo. If we instead, we can start to assemble bunches of these together in some way, in some case a hypothetical node, or certainly on a small number of cores, like on a Sandy Bridge node, then this can go up to a 16 by 16 by 16 cube, with the halo now is shrunk down in terms of it's still the halo around the entire area, but we don't have the middle halo, and then we could have only 30% halo. If we, in theory, had a 64-core node, where we could put a thread for each one of these things instead of using processors, then we may be able to shrink it down even further. And this becomes a real problem, or something we could really benefit with if we were to have an MPI OpenMP code with something such as the weather prediction model that is used here. So at the moment it runs on about 1,000 processors, about a 500 by 400 grid with 60 atmospheric levels. And that means each individual processor is a 20 by 10 grid points in 2D, the 60 high. The halo width is quite wide at 3, so that's 26 by 16 points, and 50% of those grid points are halo cells on the way that it runs at the moment. Now, code doesn't use threading. There is actually a threaded version, but it was more an experimental version, and it's going to be used hopefully as the basis for future versions for this code, if another code doesn't take over. And what this means then would be that if you could use 4 threads, you could shrink that halo down. If you could use 32 threads, you can shrink it down even further, and you would be able to free up some memory and free up some of the communication pattern, in theory. Now, replication of data is not restricted to just structured grids. There are many, many other things. Domain decomposition as a whole, you can normally make benefits if you're able to go into a hybrid mode. So that's about where we can save things. I want to just also mention about where threading can help in a completely different way, but something that you might actually have hidden from you. And that is, so the people who do MPI, how many of you do things like MPI iSend and iReceive instead of just straight sends and receives? Asynchronous communication. Anybody? Yeah? Okay, a few people do. So it looks good because you say, oh, look, I've just made a send. I'll get on with some other work, and the operating system or somebody's going to get on with this and transfer that data for me. This is normally not going to happen, okay, because it looks good, but common implementations simply don't have threads sitting in the background to move the data forward. So you may get some hardware support for this. You can put something in a buffer, say, I've got some data here to the hardware. There's a pointer to where the buffer is. Can you do it for me? And that works in places. But if you're expecting the library to help you, that's not really normally going to happen, because otherwise you'd have to have a thread, and that might interfere with you. So what typically happens is you get 2 chances to send a message. Well, there's more, but if a communication doesn't happen immediately, an MPI send or an MPI receive send the thing immediately, it just sits there and says, okay, well, I've made a record that this thing needs to be shoved out at some point, and I'll come back to it at some point. So if you don't do anything like test or any other MPI communication in the background, just to fire up the library to let it go through its processes, then the next time would actually be when you come to wait. So you really end up with only 2 chances to make this sort of call. Now, there's been some attempts to actually improve this for certain libraries, and certainly the Cray implementation has been trying to do this. It's actually MPitch who've been doing the work, a lot of it, and Cray have tried to accelerate this, and they're feeding some of it back. And this will happen if you give up a core. Now, with a Sandy Bridge node, we've got 16 cores, physical cores, and if we think about hyperthreads, we've got 32 threads. And on the Interlagos, we've got 32 cores. We really need them all. Maybe we can get away with one of them, right? This is per pure MPI implementation. I've run 31 or 15 per node, and is it really going to make our performance suffer? Well, it may be that actually it improves our performance dramatically to throw away one of these per node to allow the application to get those asynchronous messages moving forward. You also, by giving up this core, it's not busy all the time, so you also allow the operating system to not get in the way of your application. How do you do this? You set a couple of environment variables. We'll mention this one in a moment about why that's there. And then it's this asynchronous progress variable. And then you would simply say, when you do your job launch, I'm allowing the operating system and any of these other things such as MPI, one core. Just one, not two, but at least it's got the one core to get on with. In theory, you should be able to do more, but that's not currently implemented. It sets one core aside, allows asynchronous progress to go ahead, and there have been this has been going on in the last year, so the current state of affairs, so what we've seen, Cray reporting they can get out of applications. Some applications can benefit, and they can benefit reasonably well, particularly also because even just setting the -R1 to get rid of core jitter can help one application we've heard of get about a 30% speed up on about 1,000 nodes, or 1,000 cores, sorry. But it's something that you may wish to play around with and just try and say, I'm prepared to give up a core if it might help my application. Okay, so, but what if we're really in MPI OpenMP? How would we get our code to work? Well, it's really very, very simple indeed, as long as you've got an MPI library that is thread safe. So all we have to do is we replace MPI init with MPI init thread to warn the library that we're going to actually be using some threading, or actually that we're not going to use any at all. Now, there's two things that go on here that change from the standard MPI init. One is that you say required, and then you get back provided. You say, I want you to provide this level of thread safety, and the library would turn back and saying, well, I'm giving you this. Take it or leave it, so to speak. And you have to deal with that if you get something you're not happy with. So, what are these levels? MPI thread single says there isn't any threading. This is just a pure MPI process, pure process-driven MPI implementation. That's the standard application that we have. And that will always be provided. You can have thread funneled, only the master thread will make calls to the MPI library. You can have thread serialized, only one thread at a time will make calls to the MPI library. So this one, the thread funneled, is to say it's only one thread and it's always the same thread. It doesn't mean that it's thread 0 or any other thread, because the thing about thread support with MPI is that it is not restricted to OpenMP. So there is no thread 0. It's underneath, it's a POSIX thread. So it's going to have some bizarre ID if you pick out what its POSIX thread ID is. And the MPI library can't know which one's good and which one's bad, which one's been spawned by somebody else. So therefore, it's the first one that calls MPI init thread is considered the master thread. Therefore, if you actually called threading, if you spawned a parallel region, and then you went into a single region and called MPI init thread from there, for example, from OpenMP, that would be what it would consider the master thread. Thread serialized says, well, a lot of us may call the library, but only one at a time. We guarantee this. And these are guarantees you're making to the library in order for it to be able to know what it can do back. And so those are the three are pretty simple things, and they may actually be all the same. Okay, there's nothing complicated about those things, because even here, you're guaranteeing that you're effectively providing most of the thread safety, if not all of the thread safety, to the library. So the fourth one is MPI thread multiple. And this says, right, it's a free-for-all. Any of our threads can start making MPI calls as much as we want, and you, the library, have to deal with it. Okay, so the implementer then, if he wants to actually return this to you and say, I will provide that level of thread safety, has to have made the library thread safe. So it's now no longer your responsibility, thread safety, you've put it all onto the library. Now, in some implementations, but we don't really see this from what our tests look like, codes that rely on MPI thread multiple could run significantly slower. There was a time when this was really the case, as people were still learning about things, but now MPI thread multiple tends to work very well. In some cases, you might need to link in a separate library because the implementer may have said, well, look, that's actually going to slow me down, but I want to provide you with a fast library in case you don't need thread multiple, and then you may have to provide separate libraries. That was the case with Cray up until about a year and a half ago, and now it's all in the same library, and they simply just make a fork effectively of what sort of implementation they're giving you at runtime, depending on what level of thread safety they see. So in most cases, thread funnel provides the best choice because it's all you ever need and it's all you're ever normally going to use. You would simply go along, write your MPI code, and when you're adding the OpenMP threads, you probably typically put something like master around any, even if it's still in a parallel region, you'd probably have OpenMP master around your MPI calls, and that's good enough for MPI thread funnel. Just a note on the Cray systems, in order to select something higher than the default, which is MPI thread single, you have to actually pre-warn the library that in the library you're going to actually make this, this request. So what this actually means is if you don't set this environment variable, max thread safety, it will return provided as single. And people often go along and start saying, I'm going to do funneled and serialized, and then again, I don't understand why things don't work very well. So this line, sorry, I should have removed that, was a line from about 6 months ago. How do you change your job launch? Well, you set OMP num threads. You normally have to repeat some information that you provide to the batch system. So the batch system, you would say, I'm going to want this many processes, each with this many CPUs per task in Slurm's case, in which is our the batch system that you've been using up to now. And then you can set OMP num threads. And then the other thing is you should find out whether your job launcher has special options for affinity. And you've been looking at affinity just recently. On some cases, you may have to go in and actually set dirty things like shed set affinity. On the Cray, you can have the -CC option. I should also say, on InfiniBand clusters, so Pilatus is one example of InfiniBand clusters. Many of them, if not most of them, run mVapich as their MPI. One important thing there you have to do is you have to switch off an environment variable. MV2 enable affinity has to be set to 0. What this is for is because many people in MPI libraries and other libraries, they want to help you. So therefore, the mVapich people said, aha, well, by default, I expect that most of you people are going to be running pure MPI jobs. So we're going to actually help you by setting affinity as we launch the processes. And then the MPI library, it's pinned, there's nobody else interfering with your core and so on. Unfortunately, the way they set things up means that if you then create a bunch of threads, even if you've hoped to have left some space for these things, they'll all be piled onto the same core. So that's really not going to help you. You have to therefore switch this off and probably use a different mechanism to actually be able to get good MPI and OpenMP working together. So that was my 27 minutes there, and it's now back over to Ben.